quantum mechanics. Yeah, just hearing those words can kind of make your head spin, right? It's this whole world of probabilities, bizarre leaps, and uncertainty that feels completely alien to our everyday lives. But what if the story we've been telling ourselves about it is, well, just way more complicated than it needs to be? What if we've been reading the whole book backwards? All right, let's get into it.
For almost 100 years now, we've basically just shrugged and said, welp, the quantum world is weird and that's that. But a really radical new way of looking at things suggests that maybe, just maybe, the weirdness isn't really a feature of reality itself. What if it's just a side effect of the math we're using to describe it?
So here's the fundamental problem, the thing that's always been so tricky. It's this massive disconnect, right? Between the world we can see and touch and the quantum world that everything is built on. It's like they're playing by two completely different rulebooks. I mean, just look at the difference. Our world, it's predictable. You throw a ball, you know where it's going to land. It's smooth, it's continuous. But then you zoom way, way down, and you get this quantum craziness. Probabilities instead of certainties. Particles being in multiple places at once. That's superposition for you. And these bizarre quantum leaps from one state to another with nothing in between. It just doesn't feel right, you know? And that brings us to the big idea, the real mind-bender for today. What if we've been tackling this all wrong? Instead of starting with all the weird quantum rules and trying to force them to make sense, what if we flip the script? What if we start with something simple, something that does make sense, and see if all that quantum weirdness just pops out naturally? All right, so this is where a physicist named Jacob Barandez comes into the picture. He's got this really cool idea to reframe the whole thing. He's saying, hey, maybe quantum mechanics isn't some bizarre new type of physics. Maybe it's just a new way of thinking about probability. And the cornerstone of his idea is something he calls an indivisible process. Okay, so to get what he means, let's think about a normal, everyday process. The domino analogy is perfect. You push one domino, it hits the next, which hits the next, and so on. The fate of any given domino depends only on the one right before it. You can break the whole chain down into tiny individual steps. That's what we mean by divisible. It's how we normally think cause and effect works. But an indivisible process, that's totally different. Let's say a particle goes from point A to point B. In this new way of thinking, you can't just track it step by step. The outcome over at point B depends on the entire journey from point A all at once. The movie analogy here is spot on. You can't understand the end of a film by looking at one random frame, right? You need the whole story. And what's wild is that this actually makes the underlying rules simpler because they don't have to keep track of every single little moment along the way. And this has a huge consequence. If this is right, then things like the wave function, that famous cloud of probability that's at the heart of quantum mechanics, well, it's not real anymore. It's not the fundamental stuff of the universe. It becomes, as Barandez puts it, just a convenient mathematical appurtenance. I love that phrase. Basically, it's a handy tool for doing the math, but it's not what's actually going on. Okay, so if we buy into this simpler starting point, what do we get for it? Does it actually, work? Can it explain the quantum world we see? Well, the answer seems to be a big yes. And the way it all fits together from the ground up is, honestly, it's just beautiful. This is the really cool part. You start with just one basic rule from probability theory, and from that single starting point, the core features of quantum mechanics just fall out of the math. For example, the Schrödinger equation, the thing that describes how quantum systems evolve, you don't have to just accept it as a rule anymore. It just emerges. Same with something called unitarity, which is just a fancy way of saying all probabilities have to add up to 100%. These things stop being weird, random rules and become logical consequences of a much simpler idea. But wait a minute, this is all great, but it's still just math, right? It's a nice story about the rules, but it doesn't tell us why the universe plays by these rules. What kind of physical thing could actually cause this indivisible process? What's the machinery under the hood? And that's our cue to bring in a second idea. It's from another physicist, David Welker, and it's called the theory of tangled dimensions. Now, this one's a bit more out there, definitely speculative, but it's fascinating because it might just be the physical engine that makes Barandez's math work in the real world. So Welker's model gives us this absolutely wild picture of the universe. Forget everything you know about smooth, empty space. Instead, picture a universe built on a tiny, tiny grid, like a cosmic lattice. And at each point on this grid is a core made of tangled up dimensions, not just our three spatial ones, but electrical and dark ones too. And particles, they aren't tiny balls. They're actual physical kinks in these dimensions. But here's the real kicker. All that quantum randomness we see, it's just the result of this entire lattice constantly shaking and vibrating.
And boom, that's the connection. Welker himself suggests that this constant, predictable vibration of his lattice, that's the physical mechanism that could be causing Barandas's indivisible probabilities. So you have one theory that's pure math and another that's a physical model, and they might just be a perfect fit. Two sides of the very same coin.
So let's be super clear about what this means. If this combined picture is right, then the randomness of quantum mechanics isn't fundamental. It's not the deepest level of reality. It's an emergent property. Think about a tiny speck of dust on the surface of water. It jiggles around randomly, right? But that randomness is just an illusion. It's really being caused by countless tiny, deterministic water molecules bumping into it. In this new theory, the quantum weirdness is the dust, and the vibrating lattice is the water molecules. Okay, so let's put it all together. You take Barandas's indivisible process and you pair it with Welker's tangled dimensions, and what you get is a totally new story for what reality is, a whole new way of looking at everything. Let's compare. The standard story says reality is the wave function, this abstract math thing, and that uncertainty is just baked into the universe. The rules are, well, they're just the rules. But in this new story, reality is a physical thing, a grid of cores. Particles are real kinks in that grid. Uncertainty isn't fundamental, it's just the effect of the grid vibrating. And the quantum rules? We can derive them. Heck, even time might not be fundamental. It could just be the tick rate of this universal lattice. So why should you care about any of this? What's the big deal? Well, by saying the wave function isn't a real thing, you might be able to solve some of the biggest, most annoying paradoxes in physics, like the Metterman problem. It could give us a way back to a universe that makes more sense, a reality where things are what they are, and all the quantum weirdness is just a shadow cast by a deeper, hidden, but ultimately logical machine. And that leaves us with one last, kind of mind-blowing question to chew on. If the very foundation of quantum mechanics, all its randomness and its strange rules, turns out to be just a story we told ourselves to explain something deeper, what else are we wrong about? What other fundamental truths about our universe are just convenient stories, hiding a reality that's simpler or maybe even stranger than we can possibly imagine?